Cryptography. Crypto what? Cryptography. As Google would describe it, the art of writing or solving codes. From military communication to ATM cards, the applications of cryptography are endless. Even Julius Caesar used cryptography to protect his private messages. But if the text is all jumbled up, how are we supposed to understand the message? Well, there are quite a few techniques used to encode messages. In this video, we will be exploring substitution ciphers, a method that randomly replaces letters with other letters in the alphabet. To do this, we are going to use singular value decomposition, or SVD. SVD is a great way to see patterns in large amounts of data. For us, SVD lets us understand common trends in the English language, like how the letter E is the most common letter, or that TH is the most common pair of letters. SVD also tells us that vowels normally follow consonants, and that there are some letters, called neuters, which display the behavior of both a vowel and a consonant. These are the kind of patterns we will be looking for when we are decoding encrypted messages. So let's see this in action. Suppose we have an alphabet with only 4 letters, E, H, L, and O. Conveniently, we can use these letters to write the word hello. Let's say that we perform a substitution cipher on hello and it becomes ELO. To find out which letters were swapped, we will use SVD. First, we need to construct an adjacency matrix, which will indicate how many times a certain letter follows another letter. The adjacency matrix will have letters that are leaders on the vertical side and letters that are followers on the horizontal side. To get the numbers inside the matrix, we will see how many times the follower follows the leader. So for example, O follows L 1 time, so a 1 is placed in that position. We will need an adjacency matrix for both the original text, hello, and the encrypted text, ELO. Now we will use SVD to decompose the matrix into the form U sigma V transpose. U is composed of the eigenvectors of A transpose, and V, similarly, is made up of the eigenvectors of A transpose A. The U vector indicates how much of a leader or a consonant a letter is, whereas the V vector indicates how much of a follower or a vowel a letter is. To visualize, we can plot each letter. One important thing to note while plotting these is that we're using the second singular vector. The first singular vector would give us an idea of the frequency of letter usage, but by doing the second singular vector, we're seeing a deviation from the average. So we're grouping elements with similar behavior. So that means we'd be grouping vowels together, consonants together, and neuters together. As you can see, the letter H is very much a leader in hello, and E is a follower. By plotting both the original text and the encrypted text, we can see that the letters all overlap. This means that, for instance, the letter E in the encrypted text corresponds to H in the original text. Using this method, we find that E maps to H and L maps to E. But what do H and O go to? These can be found by summing up the columns of the adjacency matrices and comparing the frequencies. But what happens when we're only given one piece of text, the jumbled words? How would we go from encoded text back to readable text? The process is quite similar. First, we extract trends from the English language from a large piece of reference text. By plotting these points, we can see where certain letters are more likely to fall. For example, the vowels, consonants, and neuters are all grouped in different quadrants. By comparing where the encrypted letters fall, we can make assumptions about what letter it must correspond to. For example, the blue encrypted letter P shows similar behavior to the red reference letter N. To make this process more automated, we can measure the distance between the points. Whatever reference letter is closest to the encrypted letter tells us that the encrypted letter replaced that reference letter in the substitution cipher. Although this automated process is quick, there is definitely room for error. To get the most accurate results, the reference text and the encrypted text would need to be very long to extract the most realistic trends in the English language.
Alright, I think we're good.
Great. Okay.